Voltage can be generated by means other than rubbing certain types of materials against each other. For example, chemical reactions, radiant energy such as sunlight, and the influence of magnetism on conductors are a few ways in which voltage may be produced. Respective examples of these three sources of voltages are batteries, solar cells, also called photovoltaic cells, and generators, such as the alternator unit under the hood of your automobile. For now, we won't go into detail as to how each of these voltage sources works. More important is that we understand how voltage sources can be applied to create electron flow in a circuit. Let's take the symbol for a chemical battery and build a circuit step by step. Any source of voltage, including batteries, have 2 points for electrical contact. In this case, we have point 1 and point 2 in the above diagram. The horizontal lines of varying length indicate that this is a battery, and they further indicate the direction which this battery's voltage will try to push electrons through a circuit. The fact that the horizontal lines in the battery symbol appear separated and thus unable to serve as a path for electrons to move is no cause for concern. In real life, those horizontal lines represent metallic plates immersed in a liquid or semi-solid material that not only conducts electrons, but also generates the voltage to push them along by interacting with the plates. Some batteries, such as the common dry cell, use a rod and a paste, but the principle is the same. Notice the little plus and minus signs to the immediate left of the battery symbol. The negative end of the battery is always the end with the shortest dash, and the positive end of the battery is always the end with the longest dash. Since we have decided to call electrons negatively charged, thanks to Ben Franklin, who had a 50-50 chance of guessing wrong direction of flow and did, the negative end of the battery is that end which tries to push electrons out of it. Likewise, the positive end is that end which tries to attract electrons. With the positive and negative ends of the battery not connected to anything, there will be voltage between those 2 points, but there will be no flow of electrons through the battery, because there is no continuous path for the electrons to move. The same principle holds true for the water reservoir and pump analogy. Without a return pipe back to the pond, stored energy in the reservoir cannot be released in the form of water flow. Once the reservoir is completely filled up, no flow can occur, no matter how much pressure the pump may generate. There needs to be a complete path or circuit for the water to flow from the pond to the reservoir and back to the pond in order for continuous flow to occur. We can provide such a path for the battery by connecting a piece of wire from one end of the battery to the other. Forming a circuit with a loop of wire, we will initiate a continuous flow of electrons in a clockwise direction. So long as the battery continues to produce voltage and the continuity of the electrical path is not broken, electrons will continue to flow in the circuit. Following the metaphor of water moving through a pipe, this continuous uniform flow of electrons through the circuit is called a current. So long as the voltage source keeps pushing in the same direction, the electron flow will continue to move in that same direction in the circuit. This single direction flow of electrons is called direct current, or DC. Later we will explore electric circuits where the direction of current switches back and forth, alternating current, or AC. But for now we'll just concern ourselves with DC circuits. Because electric current is composed of individual electrons flowing in unison through a conductor by moving along and pushing on the electrons ahead just like marbles through a tube or water through a pipe, the amount of flow throughout a single circuit will be the same at any point. If we were to monitor a cross-section of the wire in a single circuit, counting the electrons flowing by, we would notice the same quantity per unit of time as in any other part of the circuit, regardless of the conductor length or the conductor diameter. If we break the circuit's continuity at any point, the electric current will cease in the entire loop, and the full voltage produced by the battery will be manifested across the break, between the wire ends that used to be connected. Notice the plus and minus signs drawn at the ends of the break in the circuit and how they correspond to the plus and minus signs next to the battery's terminals. These markers indicate the direction the voltage attempts to push electron flow, that potential direction commonly referred to as polarity. Remember that voltage is always relative between 2 points. Because of this fact, the polarity of a voltage drop is always relative between 2 points, Whether a point in the circuit gets labeled with a plus or a minus depends on the other point to which it is referenced. This circuit schematic diagram has each corner of the loop marked with a number for reference. With the circuit's continuity broken between points 2 and 3, the polarity of voltage drop between points 2 and 3 is minus for point 2 and plus for point 3. The battery's polarity, 1 minus and 4 plus, is trying to push the electrons through the loop clockwise from 1 to 2 and then 3 to 4 and back again. Now let's see what happens if we connect points 2 and 3 back together again, but place a break in the circuit between points 3 and 4. Now the polarity of the voltage drop between those 2 points is plus for 4 and minus for 3. Take special note of the fact that points 3 sign is opposite of that in the first example where the break was between points 2 and 3, where point 3 was labeled plus. It is impossible for us to say that point 3 in this circuit will always be either plus or minus because polarity, like voltage itself, is not specific to a single point, but is always relative between 2 points. That is why we always connect 2 wires to a voltmeter or multimeter when making voltage measurements. Thanks for watching.